Hey, it's Dr. J. 2.2 today. Evaluate, translate, and simplify expressions. This is really just a continuation of 2.1, so not a lot of new material in this section. It might get a little bit more complicated, but for the most part, a lot of the terminology and things that we'd learned yesterday are going to be continued. We'll start off with a little bit of what evaluate means. I know I mentioned this yesterday, but evaluate means find the value. Simplify. Do the math. Okay. And we have two basic, forms of the word evaluate. One, if there's no variables. So if you have no variables and you have some problem like this, and I'm starting off relatively simple today. So I say, evaluate the following, and there is no variable here. It's just an expression with no variable. Well, find the value. Simplify this. Do the math. Yeah. So 3 times 5 would be 15. And 15 minus 8 would be 7. So this has been evaluated. And the value is 7. Yeah. However, if there are variables, I can say something like this. Evaluate 3x minus 8 when x equals 5. It still means the same thing as 3 times 5 minus 8. It's just written in a variable form. So I would say evaluate this. So that means plug in the value. We sometimes call this a replacement value. And notice I intentionally made these the same problem. So now you are replacing the variable x with the given value 5. We already know the result, 15 minus 8, and the value is 7. So throughout this course, I will sometimes say evaluate when there's no variables. And I will sometimes say evaluate when there are variables, and they mean the same thing. It's essentially the same idea. Okay. So that's pretty much what we're doing in this section. Now that I've opened up the can of worms, we could just start talking about some examples like you might see. Got to write this carefully. In 2.2, we're going to be doing a lot of problems involving variables. So evaluate 9x plus 5 when x is equal to 3. So here's a technique that I'm going to illustrate in this section, and I hope that you take it for what it's worth. So I am replacing x with this value. Yeah. So x becomes 3. And now I'm going to calculate what it is. It's 5, which is 32. There you go. It has been evaluated. They get worse or better, depending on how you're looking at it. How about evaluate 2w plus 6p for w equals 6 and P equals 5. We have lots of synonyms. Sometimes I'll say when, sometimes I'll say for, sometimes I will say given, sometimes I will say if. Right. And math is just like any other language. We don't like to use the same word over and over and over again. We like to have a variety of words that all sort of mean the same thing. And that makes our language richer, makes it more intelligent. And you plug these values in to replace. Now this is a two-variable expression. So I've got a W and a P. So just be careful that you put them in the right place. So W is the 6 and P is the 5. So 12 plus 30, and the value is 42. I want to make sure that you understand how to say this right. This is not called the solution. All right, and I know we probably won't talk all that much. Mostly you're just listening to me, but in a classroom setting or in a real world situation, we're talking to each other about stuff. Somebody says, "Oh, the solution is 42." Well, not really, no, because you didn't really solve anything. All right, you just evaluated it. So this is called the evaluation, or you can say the final value. You can call it the result. I mean, if you really want to sound elementary, you can say the answer. But it's not the solution because we have not solved anything yet. Solving will come much later in this chapter. I don't know if you've noticed something about me so far, but I really care about how you say things and what they mean to us. It's much more important than your ability to get the right answer. It's how you present it, how you say it. Must be said right. All right, they get a little worse. Evaluate t squared minus 3t plus 7. This is back to just having one variable when t is 4. One of the biggest causes of mathematical mistakes has nothing to do with math at all. Most math mistakes are really just psychological mistakes. So you look at the problem, you try to make it the way you want it to be, and you end up making some silly little mistake. By the way, I do the same thing sometimes because I'm a person just like you. All right, any kind of mistake that you might make, I probably would make the same mistake. So one thing I recommend, it's going to be very important as we move through the chapters. Every time you see a variable, remove them and put blank parentheses where the variable used to be. All right? Because if you don't do that, you might get the right answer, but you are much more likely to get the right answer by removing and replacing, use parentheses. So remove the variable, put parentheses, and then replace with the given value. Technique is everything in this class. 4 squared is 16. 3 times 4 is 12. And then follow the order of operations. 16 minus 12 is 4. And 4 plus 7 is 11. If you really want to have good form, only work vertically. Occasionally you can move horizontally. My general rule is if you do move horizontally, suppose you move over, only do it one time. Because if you keep going over, it just starts to cause a real mess. It's hard to keep track of where you are and what step you're on and things like that. So try to move down. And if it becomes necessary to save space or to save paper, you can move sideways, one time. if it becomes necessary. Okay. Example 4. Okay, so example 4 is another evaluating. This time we'll do 3k squared z for k equals 5 and z equals 9. I typically write my z's with a slash through the middle just so that it doesn't look like the number 2. I recommend you probably do that as well, unless you're really particular about how you write them. How z's and 2's can sometimes look very similar. So I'm going to follow the same basic procedure I've been talking about. Remove all the variables. Now remember to only remove the variables. Don't remove any of the exponents or any of the coefficients. Just remove the variables. I know you're not going to want to do this because you're going to want to just take these numbers and jam them into the expression, but trust me, it's going to get a lot worse as we go through this. So everything you do now is going to, pay you back dividends later. So we're going to put 5 in for k and 9 in for z. Now we're going to follow the order of operations again. You must do the exponent first. You can do that with mental math. It's one of the little clouds I like to draw. 5 squared means 5 times 5, which is 25. So that's going to be 25. It's super important that you do that. If you try to go 5 times 9, or if you try to go 3 times 5, it's going to screw the whole thing up. All right, so make sure you follow the order. All right, at this point, it's all multiplication now. Okay, so we could probably remove the parentheses and just use dots if you wanted. So it would mean the same thing as this. Or not. I mean, you've already written them down, so you might as well just leave them there. I typically go from left to right, but remember with multiplication, it's a commutative operation. You can do it in any order, and you should get the same answer. I just do it from left to right. It's usually the simplest way. So 3 times 25 is 75. And then 75 times 9. Okay, here's that rule. See, I've kind of run out of space here, so I'm moving over one time. 75 times 9. If you already know the answer, it's 675. I really discourage you from using your calculator, especially early on in the class. There may come a day later in the semester where I break out the calculator, but that day is not today. So I recommend practicing training your brain with mental math. This is the whole reason why we take basic math. So 9 times 5 is 45. Carry the 4. 7 times 9 is 63 plus 4 is 675. Okay. All right. So this is the final value or the result. Next, we'll move on to example 5. I say fancy, I just mean I'm changing the order a little bit here. Look, I got k and then x, but then I gave you x and then k. So just be careful when you write your expression. Make sure you know who goes where. So k is going here in the first spot, and x is going here in the second spot. You're going to get sort of in the habit of doing these problems, and usually they go in order, but sometimes the order is reversed. Remember to always follow the order of operations. So 3 squared is 9. 5 times 9 is 45. I'm running a little low on space, so I'll go over here and say 47 is my final answer. I guess I probably could have fit it down here. But this is what I mean about, it's okay to go sideways, once, right? But I wouldn't want to keep going like this and end up off the screen or end up over on a side scratch paper or something like that. You wouldn't want to do that. All right. It's the little things. All right. We start building those habits now in this class, you won't suffer as much in the future. All right. Okay, so that's it for evaluating. Next, we're going to review translating. Many of these problems we've already done, or we've done problems similar to these. So feel free to fast forward if you feel like this is redundant. But I just want to make sure I cover this as many times as I possibly can. Because the comment that I often get, and I think I even got a few email comments this first week, they'll say, Dr. Jordan, I'm really good at doing the math, but it's the word problems that get me every time. So if you're one of these folks out there that, is like most of us, and that you can do the math if the math's all set up for you, but once it comes to the word problems, we end up in a lot of trouble, then I want to make sure that for those people, I'm giving it double coverage or maybe even triple coverage before we get too far down the road. So Marcus bought T children's movie tickets. The movies were even open yet. $5 each. And P, adult tickets, I'm just going to abbreviate TICKS, for $8 each. Now write an expression for the total Marcus spent. Now, I'm doing this intentionally to sort of give you lots of different variables. I don't want you to be too comfortable always having X and always having Y. So I'm using variables like T and P. But I want to be perfectly honest with you. At some point, we're going to choose our own variables. All right? I'm not letting you pick your own variables right now. All right? I'm picking for you. All right? So you have to use the variables that I've picked. But at some point in this class, I'm not going to be picking what you have, right? You got to grow up and mathematically grow up and choose your own adventure, right? Or choose your own variable. So honestly, I probably would have used C for children and A for adult. That's what I would have picked, but I didn't. I picked P and T because I just want you to deal with the variables that I'm choosing for you. So the expression is 5 times T. Yeah, $5 times T. We may omit the dollar sign. Yeah, it's not necessary. As long as you know this represents dollars. And then plus $8 times T. And then simplify this. Oh, sorry, $8 times P. Adults are P. And then simplify this by removing the dots. However, if you keep the dots there, or if you use parentheses, I would still mark it correct. You could also do it this way. Yeah, so I would accept it with dots, I would accept it with parentheses, or I would accept it with neither. Yeah. Just remember, don't use an X anymore. We had a lot of problems with the X, I noticed back in chapter 1. Anyway, we'll talk about that later, but the X really does start to cause problems. Oh, there goes my my blurry. There we go. So example 7. So example 7. The length of a rectangle is 5 inches less than twice the width. Write an expression for the length if the width is W. So this is more, common sense mathematics. If I'm talking about width, I like to use W. Yeah. Now it did say an expression, not an equation, an expression. All right. So we're not even going to use the letter L. All right. Do not use the letter L. All right. If we use the letter L, it would not be an expression. It would be an equation. So we've got 5. Now, inches, we can omit inches. We know in our mind it represents inches. Less than twice. Twice means the same thing as double. Yeah? Double, twice, multiply by 2. So 2W, yeah, because it's twice the width. And then less 5. Yeah, less than means subtract. So this is an expression for the length. All right, I don't want to say L, because if I say L, then I'm making an equation, not an expression. Expression for the length. All right. One more? A lot more than one more. How about one more of these with the rectangle? The length of a rectangle is 5 inches less than twice the width. If the width is W, find an expression for the perimeter. It's getting a little tougher now. We did talk about perimeter before. Remember what perimeter means? It means perimeter, peri, outside, meter, measure. So we're going to measure the outside. Okay. Now, I don't want to use the letter L. All right. I can only use the letter W. Okay. So you must only use the given letter. So there's no P's, can't have a P, can't have an L. You just want to have W's. All right. W is typically the shorter side of the rectangle. All right. When you're drawing a rectangle for an algebra problem, you might as well just call W the smaller side. Now, since we've already solved this one yesterday, 10 seconds ago, example 7. In example 7, we already did this. It's 5 inches less than twice the width. So these are the long sides, 2W minus 5, 2W minus 5. It's a rectangle. Yeah, so it has these sides on both of the longer sides. Those are your lengths. You don't want to put a third letter in here and have it say L. You also don't want to put a P in here. All right. So what is the perimeter? The perimeter is to add up all the sides. So I've got 2W minus 5. All right. I'm going to go around this way. And then plus a W. Keep track of where I'm going. Plus another 2W minus 5. Plus another W. And it really doesn't matter where you start. I started at the top and went around this way. You can start anywhere you like. Just make sure you don't double count anybody. All right. So these are what we call like terms. We're going to combine the like terms. I'll give you a more precise definition of like terms in a minute. For now, just think of like terms just means that they have the same letter. They're like. Yeah, that's one of the reasons why we only want to use one letter. 2 W's plus 1 W plus another 2 W's plus another 1 W is a total of 6 W's. And then I got the minus 5 and the minus 5. That's going to be minus 10. So this is an expression for perimeter. It's not an equation. In fact, this equal sign is really not even there. I put the equal sign just to tell you I'm working the next step, but your final answer doesn't even have an equal sign. It's an expression. It just says 6W minus 10. Okay, can you see that? Kind of hard to see, isn't it? There we go. That's your expression for the perimeter. All right. A couple more of these translation problems. One thing I should mention is we're not solving. Yeah. I'm not finding out what W is. I'm not finding out what L is and the length. I'm also not finding out what the perimeter is. So we're just practicing expressing ourselves. It's like the language of mathematics. We're just practicing using the language. Eventually, we will use this language to actually solve a problem and actually come up with an answer for something. You can't solve something until you know how to speak the language. The language of algebra. Jane has 2 trees in her yard. One is 15 feet taller than the other. Let H be the height of the shorter tree. Find an expression that represents the sum of the heights of both trees. Okay. So we've got one tree. And we've got a shorter tree. You can tell I live in the desert. These are palm trees, yeah. We're going to let H represent the height of the shorter tree. So this is going to be H. One of the trees is 15 feet taller than the other. So this one is H plus 15. It's the taller one. All right. The sum is H plus 15 plus another H. So I'm just adding these two guys together. Add these two guys together. And then simplify. H plus H is 2H plus 15. Okay, that's probably enough. If you need more examples of translating, you can go back and review 2.1. I did a ton of them in 2.1. I just wanted to cover a few of the loose ends, maybe a few of the problems that I didn't cover in the last one. And then I like to just leave a few of them out there. You know, I like to leave a few dangling so that you can kind of figure it out, piece it together, and gives you something to work for a little bit. So I think we're done for now. We'll come back with that. Next, I'm actually going to define like terms. Okay, first of all, we're going to talk about terms. Terms are separated by either addition or subtraction. So, you know, 5, 6x, 3, 7x, something like that. So these are called terms. Okay. I actually like to include the sign with the term. All right. If there is no sign, then it's positive automatically. So if you don't see a sign, it's an automatic plus sign. So these are called terms. Like terms are terms that have the exact same variable or variables if there happens to be more than one. Exact same variable, the exact same power or exponent, also known as powers, or they have no variable at all. Those are called constants. So for example, 5 and -3 are like terms because they are constants. So yes, these are like terms. They are both constants. Yeah. 6x and 7x, those have the same variable. They also have the same exponent too. If you don't see an exponent, it's an invisible 1. If there's no exponent, then it is invisible 1. Yeah. So technically, there's a little invisible 1 right there. 6x to the 1 power, the first power. And over here, 7x to the first power of the first power. So that would be the invisible 1s if you really want to be picky about whether or not there's an exponent. Whether or not they have the same exponent, I mean. Okay. So simplify means to combine all possible like terms. All right, so let's do an example. Example 10. 3x squared less than 4x cubed. So first we translate. Remember, less than, we want to reverse the order. So the 4x cubed comes first. The 3x squared comes second. Simplify. Combine if possible. Yeah. Since the exponents are not the same, look, one of them's a second power, the other one's a third power. We can't combine, so it's already simple. Yep. So that means this is the answer. 4x cubed minus 3x squared. That's it. It's already simplified. That's what we say, as good as it gets. Yeah? It don't get no better than that. That's as good as it gets. Example 11. 2x to the fourth more than 5x to the fourth. More than means add and keep the order the same. Keep it in that same order. Remember, addition is commutative, which means you can change the order if you want, but it's not going to change the answer. Okay? Less than is not commutative. With less than, you have to change the order, otherwise you'll get it wrong. So just keep it in the same order. 2x to the fourth plus 5x to the fourth. Combine if possible. Yeah. Well, look. Same variable. Same power. Power, exponent, tomato, tomato means the same thing. Now here's the thing, if you haven't had algebra before, or if it's been a long time since you had it, 2x to the fourth plus 5x to the fourth is 7x to the fourth. You're going to add the coefficients, not the powers. All right. So it's 2x to the fourth plus 5x to the fourth. When you add them together, you have 7x to the fourth. One way to think of that mentally is think of x to the fourth as an intangible object. It cannot be broken into smaller pieces. Right? I mean, you can't hold it in your hands, but you can think of it as a tangible object. Well, if you had 2 of these things, and then you added 5 more of these things, when you add them all together, now you've got 7 of these things. Yeah, so these 7 of whatever these things are, this, intangible object called x to the fourth. simplify. 3y squared plus 4y squared, excuse me, 3y squared plus 4x squared plus x squared. All right. These are the like terms. Yeah. This one's not like. Yeah. It doesn't have any other like terms. There are no other y's. It's not the same variable. There's also an invisible 1 invisible coefficient of 1. All right. So keep that in mind. When you combine these, the 3y squared is just going to come down, but these guys are going to add together 5x squared. That's as good as it gets. Don't try to combine an x with a y. All right, they're not like terms. All right. Simplify 6z minus z. I've seen this before. Don't do it. That'll cause you a lot of problems. And I can see why somebody would do that. I mean, it intuitively makes some sense. You have 6z, and then you take away the z, so you're going to have 6. Yeah, that's just incorrect. The correct way to do it is to put the invisible 1 in front of the z, and then think about it again like an object. You have 6z, you take away 1z, and now you have 5z. I don't know if I have enough room to do one right here, so I might need to erase again. Okay, let's simplify this. Now here's something I want to make very clear. When you combine the like terms, include the sign here to the left. All right. I don't want you to accidentally think of that as being a 4 by just chopping off the negative sign. I have seen students accidentally apply the negative to the number, to the 5 here. All right. The 5 is positive, and the 6 over here is positive. You can do all of these with mental math. So you have 7 of these like terms minus 4, so that gives you 3. And remember not to change whatever the power is. You have 5 plus 6, so now you have 11. 5 plus 6 is 11. And remember not to change the power. Okay, we're going to wrap this up with some geometry. there was a time where we wouldn't do any geometry at all. We would just do a whole bunch of arithmetic and beginning algebra, and then all of a sudden we dump a whole bunch of geometry on top of people. And it turned out to be quite crushing for most people because they just thought, oh, I was doing really good in this class until the geometry came. So a new approach, at least that I've been implementing, is I just squeak the geometry in little by little, give you little small doses of it until you build up a tolerance for it, sort of vaccinating you against geometry. And then when we do finally have a more extensive section on geometry, it won't be so bad. So example 15, the perimeter of a triangle is 40 centimeters. Two of the sides are 5x and 3x. Find an expression for the other side. Okay, so the perimeter is 40. I don't really need the centimeters yet. I mean, if you were to measure this, it would be measured in centimeters, but that's just off to the side. We really care about the number 40. Okay, and then the perimeter is adding all of these guys up. Yeah, so you'd have the total is 40 minus the 3x minus the 5x, and this expression would give you the missing side. The perimeter is the total. So if you take the total is 40, and you subtract both of these sides, that would be your expression. And now you want to simplify this if possible. So it's 40. Are these like terms? Yeah, they both have the same variable. So minus 3 and then minus 5 is minus 8x. Think about it like a credit card, right? If you spent 3 and then you spent another 5, altogether you've spent 8. Sort of like negative numbers, but technically none of these numbers are negative. But it kind of has the same concept. We're going to get more into the negative numbers in the future. In this section, I'm just thinking of it as subtracting. If I subtract 3 and then I subtract 5, altogether I've subtracted 8. So this is the answer. Suppose the sides of a rectangle are 2x plus 7 and 3x plus 2. Find an expression for the perimeter. Let's just give it a second. I don't know how long it's been doing that for. Give it a second. I'm not stopping now. Come on. We're so close to being done. Don't do this to me. Come on. There we go. So suppose the sides of a rectangle are 2x plus 7 and 3x plus 2. Find an expression for the perimeter, the entire perimeter all the way around. All right, well, remember it's a rectangle. So if you have a 2x plus 7 on this side, you also have a 2x plus 7 on that side. Yeah. If you have a 3x plus 2 on this side, you also have a 3x plus 2 on that side. Perimeter is the total, so add them all up. In this case, we're not finding the missing side like we were with the triangle. I just want to add all these things up. So we're going to go all the way around like this, add them all up, add them all up, add them all up, and know when to stop. I'm starting right here, so I've got 2x plus 7 plus 3x plus 2 plus another 2x plus 7 plus another 3x plus 2. If you're really clever, you'll group the 3x plus 2s and the 2x plus 7s, but I'm just going around as if I'm running around the track, you know, just going around one lap around. Perimeter, yeah? So I've got 2x, 3x, another 2x, and another 3x. Combine all those like terms together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 x's all together. And then I've got my 7, my 2, another 7, another 2. This is what I meant about grouping. I could have just grouped the 7s. That would be 14. And I could have grouped the 2s, but I didn't. So I've got 7 and 2 is 9. 7 and 2 is another 9. So I've got 10x plus 18. So this is the expression for perimeter. Yeah, not too bad. Again, we're not solving for x. We don't really know what x is. It's fine. We'll find out what x is later in this course. It'll probably be a slightly different problem, but eventually we'll solve for x. Right now, we're just expressing our language. Just a couple more. Next, we're going to talk about volume and area. Remember, area is the inside of the rectangle. Sorry, my rectangle doesn't look very straight. It's because my camera is tilted at an angle, so you're seeing a kind of a skewed version of it. Let's see if I can make it look a little straighter. There we go. All right, if this side is x and this side is y, the area is x times y. Or you could just say xy. That's it. This is the expression for area. Okay. That said 7. I meant 17. That was example 17, not example 7, obviously. Find an expression for volume. Volume is when you have a three-dimensional object. Like an aquarium or a box or something like that. So volume is how much water or stuff would fit inside. It's also called capacity. Yeah, how much does it take? How much can you hold inside of it? Well, the volume is the length times the width times the height. Or you could just say LWH. It doesn't matter what order you multiply. I say this a lot. Multiplication is commutative. So if you scramble the order, if you do WHL or HWL or whatever you like, it will still give you the same. We typically memorize it LWH, though. I don't know why. It's not even alphabetical, right? I guess alphabetical would be HLW, right? Height times length times width. How about this? Find the volume suppose this is 9 centimeters, and suppose this is 4 centimeters, and suppose this is 6 centimeters. So this is not very big. This would be, I don't know, a little teeny, fish tank that sits on your box, or on your sits on your desk. One of those little tiny little ones, like you sell at Petco or something, It's very small. It holds one fish. Right, so you got one fish swimming inside of here. Okay. So the volume, you multiply 9 times 4 times 6. And you could do it in any way you like. 9 times 4 is 36. 36 times 6, 216, I think. If you're not sure, do it the old-fashioned way. 6 times 6 is 36, carried the 3. 6 times 3 is 18, plus 3 is 216. Check. Now check this part out. I'm going to start bringing inside the centimeters into the answer. This is centimeters times centimeters times centimeters. You're multiplying all these centimeters together. So that's called centimeters cube or cubic centimeters. So that would be your answer, 216 cubic centimeters. If this was a bigger tank, suppose it was measured in inches or feet or even meters, then it would be 216 cubic feet or 216 cubic meters or whatever it happened to be measuring with. Inches. If it's really big, kilometers or something, that'd be really big. Okay. Whew. Coming up on an hour. Last example. Find the surface area. Same thing, same tank. 9 centimeters, 4 centimeters, 6 centimeters. Now this one's going to be a little trickier. The surface area would be like if this thing were made out of glass, all 6 pieces of glass. All right. Now let's think about what an aquarium or a box sort of looks like, right? You've got this piece of glass right here. surface area, so it's the glass, yeah, or whatever it's made out of. If it's made out of wood, then these are made out of wood. All right. But don't you have another one of those over here? Right? If you have a front piece of the glass, you have to have an equivalent back piece of the glass. So the surface area, front and back, is 6 times 4 plus another 6 times 4. Right? So that would be 24 plus 24, which is 48. Let's just save that guy for later. So 6 times 4 is 24. That would just be the area of this piece here. Add those together. You got front and back. Okay. And there you go. All right. Well, you also have side, and then you've got an equivalent side over here. I know it's getting really messy. Maybe if I get rid of the blue, it'll help. So I've got this side back here that's in red, and this side that's in red. And let's try and get rid of some of that blue. So I've got area, side, side. I'm calling this front and back. I'm calling this side, side. And then I guess I'll call the last of it top and bottom. All right, so what would that be? This would be 9, and this would be 6. Yeah, this is 6. This is also 6. So it would be 9 times 6 plus 9 times 6. 63 plus 63, 126. Save. All right, so that's this big red side and then the other big red side. They're both 9 by 6. Okay, and then finally, just draw this one more time. I've got top and bottom. So I've got the top, the lid, and then I've got the floor, the bottom. All right. So what was this? This was 9. Yeah, and then this was 4, right? It was 9, 4, 6, right? So if we're doing top and bottom, it's just going to be 9 and 4. So it'll be 4 times 9 plus 4 times 9, 36 plus 36, which is 72. So finally, the surface area. So how much surface covers all of this? Just add all these up. 48 plus 126 plus 72. Let's see, that would be 14, 15, 16, carry the 1. 5, 7, and another 7 would be 14, carry the 1, 246. And that would be square centimeters. Because we're not talking about the inside, we're talking about the outside. So the answer would be 246 square centimeters. Okay, everybody, we're done for week 2. Until next time, this is Dr. Jordan reminding you, do your homework. See you on the internet.